In this video here, we're going to take a look at using the root inspection algorithm. Now, the root inspection algorithm, or sometimes called the Chinese postman algorithm, can be used to find the shortest route in a network that traverses every arc at least once and returns to its starting point. And we can easily solve this problem if the network is Eulerian. Now, if all the vertices in the network have even degree, then the length of the shortest route will be equal to the total weight of the network, right? Which is pretty straightforward. Now let's just take this network here to our right, that's this network here, as an example. Now by inspection, then we can see that all the vertices in this network have even degree, right? So this vertex here has degree 2, this one here has degree 4, this is degree 2, this is degree 4 here as well, and this one here has degree 2. So what I've got here then is an Eulerian network. So therefore the shortest route is equal to 6 plus 7 plus 10 plus 3 plus 5, so on and so on. Basically, just add all the values here together. That should be pretty straightforward. And we get 67. Okay, that is the total weight of the network. And a possible route here would be the following. So ABC, so on and so on. I won't bother reading out the full route. It sounds like I'm learning the alphabet for the first time, but you get the idea. Okay. Now, what about if our network is semi-Eulerian? Now that poses a bit of an extra problem. So let's just take a look then at how we can adapt the root inspection algorithm to deal with this problem. So if the network is semi-Eulerian, we need to traverse some edges more than once. And if a network has exactly 2 odd vertices, then the length of the shortest route will be equal to the total weight of the network plus the length of the shortest path between the 2 odd vertices. Now, if the network has more than 2 odd vertices, then we need to consider all the possible pairings of the odd vertices. We then need to include additional arcs to join the odd vertices. And we then select the arcs with the smallest, I can't speak anymore, with the smallest total additional weight and add this to the total weight of the network. And this method produces an algorithm that can be used with any connected network. And more formally, the root inspection algorithm is as follows. So for step 1 then, we start by identifying vertices with odd degree. Step 2, we then consider all the possible complete pairings of these vertices. For step 3, we then select the complete pairing that has the least sum. And then finally for step 4 here, we add a repeat of the arcs indicated by this pairing to the network. Okay? As you can see then, generally speaking, the root inspection algorithm is pretty straightforward. Okay? So that concludes this introduction here to the root inspection algorithm. As always, I think the best way to really demonstrate this algorithm here is to work through a practice question. So let's just get started then with this practice question here. So let's just get started here then with this practice question. Now for this question then, what we're told here is the diagram below shows a network of underground cables connected to 6 different villages. So the nodes here represent the different villages. Now, the number on each arc is the length in kilometers of that cable. And a route of minimum length is required that traverses every cable and starts and finishes at F. So, starting at F here, we then traverse every cable and then finish at F. Okay? Now, for the first part of this question, so that is part A, all we want to do here then is just state the cables that will need to be traversed twice. Now, clearly, we're going to use the root inspection algorithm here. That's the whole point of this question, right? But clearly, that's what we need to use here. So if we're going to use the root inspection algorithm here, the first thing that we need to do then is just quickly denote then the order of each vertex. Now, if you want to do a table, that is fine. But just in the interest of saving time, especially in an exam, what I would quickly recommend that you do here is just denote the order on the diagram or on the network here. Okay? So to do that then, for example, starting with vertex A here, I can see then that vertex A has order 3. So all I'll do here is put a 3 next to it, right? We'll put a circle around it, just keep it neat. So vertex A then has order 3. Vertex B has order 2. Put 2 in a circle around it. Same for vertex D here. That also has order 2. Vertex C has order 4. Like so. Vertex F has order 2 as well. And then finally, the very last vertex here, vertex E has order 3. So if I just go back to my original pen color here, what I can see then is this network here is actually a semi-Eulerian network, right? We have two odd vertices. So, I'm going to make a note here. This network is a semi-Eulerian network. So this network is a semi-Eulerian network. Now, why is that important? Well, in that case, then we just have two odd vertices. So what I need to do here then is find the shortest path connecting my two odd vertices, right? A and E. So let's make another note here. So the shortest path then. So shortest path connecting my two odd vertices. So connecting, that would be A and E for this question here, is going to be, so let's just quickly look at the diagram here. We can just do this by inspection, right? So I can see then that the shortest route here is going to be from A to C and then C to E, right? That will have a length of 10. Clearly, we're not going to go from A to B, B to C, C to D, and then D to E, because for example then, A to B has a weight of 5, B to C has a weight of 4, so that's 9. C to D has a weight of 6, so we're already at 15, which is greater than 10. So clearly that won't be the route there. And then same again along the bottom here, so A to F has a weight of 12. It's already greater than 10. So the shortest path connecting A and E is going to simply be A, C, E. So A to C and then C to E. And that has a length of 10. So with length 10. Okay, I won't forget the units here. I'm working in kilometers. So with length 10 kilometers. Okay. So in that case then, let's just quickly finish the solution to part A. So for part A then, it said state the cables that will need to be traversed twice. So what that tells us then is the cables that need to be traversed twice are AC and CE. So therefore then, cables that need to be traversed twice are, so like we just said then, AC, so AC and also CE. Perfect. Good stuff, right? As easy as that, that is the solution to part A. And now for the second part of this question, it says, well, this is for part B. It says, hence or otherwise, determine the minimum length that starts and finishes at F. So basically now, just implement the algorithm. So for part B here, we'll do this underneath. Let me just quickly add to my diagram here. I'll do it in, let's do it in blue here. What I'm going to add then is the extra arc to my diagram. I want to quickly explain what's actually going to happen here. So we go from A to C. So I'll add the extra arc on like so. That has weight 3. And again, we repeat this arc here, C to E. My diagram isn't going to be the neatest, but it doesn't matter too much. And this arc here will have a weight of 7. Now, why is that important? But once we repeat these arcs here, it actually makes this network go from a semi-Eulerian network to an Eulerian network. Basically, all my vertices here now are of, when I can speak, are of even degree. So rather than having two odd vertices now, all my vertices are even. So in that case then, the minimum length here is just going to simply be the sum of everything on this network. Or you can also think about it as the total weight of the network before we added these arcs here, plus the shortest pairing, right? Sorry, not the shortest pairing, but the shortest path here. I'm kind of thinking of when you've got 4 odd nodes there, so just ignore that. Just the shortest path here connecting my two odd vertices, okay? So let me just make a note here. I've got blue pen, right? I want black. So in that case then, let me make a note here. The total length, so the total length of the route this is equal to the total weight of the network. So total weight of the network. Now, normally for a question such as this one, where you do need to use the route inspection algorithm, they will just give you the total weight in the question. Given that the network here is pretty simple, I didn't bother doing it for this question. But like I said, in an exam, they will always give you the total weight of the network. They won't expect you to kind of work that out on the spot. Not that it's complex or anything, but just to save you time in an exam. And also the length then of ACE. So plus the length. So plus length of ACE. Okay. Now the total weight then, I already worked this out here. So that's going to be 5 plus 3 plus 4 plus 6 plus 7 plus 9 plus 10 plus 12. That is going to be 56. So we get 56 there. And the length of ACE, as we deduced in part A, is 10, right? I get 56 plus 10. 56 plus 10 gives us 66 there. Okay, so we get 66. Don't forget our unit, so 66 kilometers here. Okay, and there we have it then. So hopefully nothing too challenging there. Now, as you can see, in the introduction, we worked through an example of an Eulerian network and using the root inspection algorithm. As you saw, that is incredibly straightforward. This example here is when we have a semi-Eulerian network where we have 2 odd vertices. The only other example here that we haven't seen is when we have 4 odd vertices, right? So it's neither Eulerian nor semi-Eulerian. So what we're going to do then in the next video here is cover an example such as that one. Okay? So there we have it then. That gives us the solution to the one practice question for this video here. And that brings us to the end then of this video here on using the root inspection algorithm.